Hello everyone. Today we will start our session by solving questions. Previous sessions we just discussed the theory. So from today itself, we'll start solving questions so that you can perform well in your exams. So our first question is related to the something called as left hand limit. The idea and the notion of something called as left hand limit. So first in the question you can see we have given to us a definition of function in which when x is not equal to 1 is defined in this way, if x is equal to 1 is defined in this way. So basically what we see here is that there is a function given to us and we just wanted to figure out what is the limiting value of this function at x equal to 1, but you are approaching from left hand side. There are two ways you can approach to a given point in a curve. Now let's say you have a function which is defined in this way and you wanted to figure out what would be my limiting value at here, because according to the definition it is given something as 4 to me, which is here, right? So what you're trying to do, basically trying to approach this particular red dot from left hand side, okay? Because that's what mean, when you're trying to approach x which tends to 1 minus. So that's the idea. So in order to solve this question, we will start using the definition which is given to us, and since we are not exactly at x equal to 1, so we'll use the definition for this, which is equal to the f of x is x square minus 1 over mod of x minus 1. But we know that in this case my x minus 1 is negative. If my x minus 1 is negative, then my mod of x minus 1 going to be open as this way, right? Because this is how the mod function works. And if you are not familiar how the mod function works, so here is your diagram. You can see from here, let's say here's a mod function x, this is x and this is 0. So you see that, let's say you have a function mod x. So mod x has two branches. The first is just x, another is minus x. So it's just open as same as it is when the input of this modulus function is positive. But if the input of the modulus function is negative, you can see it picks up a negative sign. So basically what happens here, we just had this line which is y equal to x, but this side got reflect, okay, just to make it positive. So that's what this function captures. It just basically captures distance, okay? That's why it is always positive. That's why you say that mod x is a positive quantity always, because it picks up a negative sign extra such that it makes everything overall positive. So we'll use the same property to solve this first question. In this case, we see that the denominator inside the input of this mod function, the denominator was the negative. So this mod function makes it positive. So to make that positive, it picks up a negative sign which is shown here. Okay. So what do we see now? We see that my f of x is just equal to x minus 1. I have just factorized the numerator in this fashion, and my denominator is just minus of x minus 1, and which I see that it just cancel out. So we just cancel out the part which made us to have this indeterminate form. You know, this function was behaving like as it is 0 by 0, right? But now we see that it's no longer a 0 by 0 form in this case, because as we approach 1, in this case, yeah, the value of the function becomes minus 2 in this case, right? So what do we see here? We see that the value of this particular left hand limit turns out to be minus 2. But you can see the value which is defined in the particular formula over here is 4. So what do we see that here? We see that in this case, my f of 1 is not equal to the left hand limit. Okay, so you can make it, you can do some regularization over here by just by defining the 4 to some -2 to make things proper. Okay, so that's another advanced level of question. For now they just have asked you what is the left hand limit, so this is how you calculate, right? So you can see here I have used just a simple property of determinant, sorry, modulus, to basically cancel out this factor which was leading me to 0 as a 0 by 0 form. So that's the idea here. I hope this first question solves everyone. I mean, everyone is okay with this first question. Now let's get back to the next question. In the next question, you can see again you have a function which is defined in the previous way, which is in the terms of modulus, and now they have asked you to calculate various limiting values. Okay. Uh, I want you guys to focus here and try to solve along with me so that you can get the idea. Because until you don't write it on paper, you will not get how to solve the problem here. What we see here is that we have another function, which is 2x square minus 3x over mod of 2x minus 3. And the first question they have asked me to calculate this limiting value. Here you can see we are basically trying to approach 1.5 from the right hand side because of this plus. Okay, you can see from here. So we will try to solve this limiting value at x tends to 1.5 from the right hand side. So we know that this particular mod function which you see here, this particular mod function has two branches. The first branch is equal to the 2x minus 3 and the second branch is minus of 2x minus 3. So when the first branch occurs, when the second branch occurs, the first branch occurs when the input of the modulus function over here is positive, right? So whenever 2x minus 3 is positive, so which tells me that basically x greater than 1.5. That means for x greater than 1.5 or equal to, you can say both, I have this particular behavior. But for x less than 1.5, it opens up with the extra negative sign here. So now you see that because of this, my original function has two branch. The first is 2x square minus 3x over 2x minus 3, and the another one with just extra negative sign over here. And each branch is valid for a given condition. The given condition is over here, which we have just discussed here. Okay, and now you can see that over here you can find some factorization. You can do some factorization to further factor down this, and once you just did all the factorization, this will turn out to be, this will,
I didn't get that. Could you try again?
so it just turns out to be, just take a common x, you will see 2x minus 3. I'm just doing simple factorization, nothing more. And over here you have minus x, 2x minus 3. That's it. Okay. And just you have to do the simple calculation, like simple cancellation, because this can get cancelled. And the reason why we can cancel, because these quantities are not exactly 0. They are very close to 0, but they are not exactly 0. And since they are the factor which was responsible for undeterminate form, at the moment you cancel them, you're left with just this. Okay, it's x and minus x. So you can see here, how this function works here. And since you were asked for x 1.5, right? So just substitute 1.5 here. And where you will substitute? You will substitute over here. right? Because you were asked for the 1.5 plus. So basically my 1.5 plus is nothing more than that. Basically it's 1.5 plus h, where my h tends to 0, right? So you can see this way, right? So we will substitute that 1.5 over here, and this will give me my limiting value. Okay, but not this. So you need to be very careful in this case. So what we found that this particular limiting value turns out to be 1.5. That's it. Plus 1.5. Okay. And I'm emphasizing it is plus, not minus. Okay. So this is how you solve this particular A part. Now we will jump to the B part. By the way, I have uploaded all these questions in the Google Drive. Same link which you have been already received. So we'll go to the next part. In the next part, exact same question, but instead of right hand side, you are approaching from the left hand side. So what we found that the function had the two branch, which was the x minus x for the x greater than equal to 1.5 and for the x less than 1.5. And the way you can find this by substituting here, right? Because this is where you can have that 1.5 minus, because that's mean that you have 1.5 minus h, where h tends to 0. So the moment you found like which branch I have to substitute, you will get your answer, and the answer turns out to be minus 1.5 for the B part. If you guys have any question, you can ask me or you can text me. Feel free to ask questions. Okay. For now, I just have you know uh, presented you a couple of questions, and we just want to understand whether this is solvable or not by you, because you might expect such basic question at least. And the last part is very simple. This just basically tells you that the limit exists or not, because the first part basically tells you that's a right hand limit, the second part is left hand limit, and we see that right hand limit is not equal to the left hand limit, and hence limit don't exist. Okay, so the answer is in this case that limit don't exist. Okay. And in case if you're wondering, we just saw the first question, which turns out to be -2. To those who in case missed the part, so we have solved 13th and 14th. Okay. I will solve this question next time, because I want you guys to have a try. I just want you to guys to try this question at least once. In the next session, I will discuss this. Okay. I can give you a hint that the L square turns out to be 100. So that's a hint. Okay. So basically, what you hear is that what you have over here is that you were just trying to understand basically the limiting value of this sequence here, and in the question they have told you that the limit exists, and you need to calculate what is the limiting value in this case. And why I have choose this question, because you can approach a limiting value, maybe not in a continuous fashion, but you can approach that value in a discrete jumps, such that if you make a jump, if you make a progress in a discrete manner, you will get as close as possible. Okay, so that's the idea. I can give you another hint why we have limit in this case, because what you see here that we have this particular recursion. We actually call this as a recursion. In case those who don't know this is called as recursion, or you can say recursion formula. It just basically tells you that if I know what is my previous value, I can write down my next value. Okay, so this recursion formula basically tells you that, let's say you had this, you have this now, and here you can see previous. So basically this is how you can write down. And basically what you have here, nothing more than that, basically a sequence. This might be a sequence of function in the sense that let's say you have a function, but in the case of input where you used to give a continuous variable, but now you are trying to give something called as a discrete. Okay, so now basically the discrete inputs, and these xn's are basically what my sequence, which can be seen as x1, x2, x3, such that xn. Okay, so that's the idea, and the reason why we are interested in this, because this is one of the technique, one of the method to approach a limiting value. So this is all about, I've told you this. The main point that I want to emphasize, that why limit exists in this case, because if you just take a ratio xn plus 1 over xn, which turns out to be half plus, half times 1 plus 100 over xn the whole square. Okay, and since your x1 was 100, we can recreate your further terms over here, and if you take n tends to infinity, you will find that my xn over xn turns out to be 1. That means the moment you are increasing your step size, like for example n, the moment will come when all the terms will be same. Like for example, that's 150, for example 30, 20, blah blah blah. Let's say now it is 50, now 5. Now what happens, if you go to the next step, again this will repeat 5, it will start repeat. Okay, so basically what the question is basically trying to ask you is that what is that limiting value after which you get the same numbers, right? So I want you guys to have a try this question. I'll discuss this next time, like how to get the answer, because I've told you the answer is L square is 100. Okay, so definitely L is root 100, which is 10. So the answer is over here, is that L square is 100. We can further investigate this. Now we'll go back to the problem set, and we will discuss this question number 24, which you can see here. Don't take these numbers very seriously. Basically, I have picked them from various sources and made a collage of all the questions so that we can have a good discussion, because I don't want you guys to have a repetitive questions to solve. I want you guys to focus on how to solve this kind of question which you face in just in case. Okay, now we have this particular problem in which they have asked you to solve this limit value, and they just want to know what is the number b such that this limit exists. Okay, so that's the idea here. So the idea over here is that you can see here the numerator is a polynomial, denominator is also a polynomial, and the way you can have existing value is that because if you see very carefully this denominator approaches to 0 as x tends to minus 2, right? So so the way you can solve this problem by doing factorization, and you can figure out that we have something called as a factor. Something, if we factorize this x square plus x minus 2, that turns out to be x plus 2 as another factor in this case, and the another factor is just x minus 1. So you can pick your b values such that if you factor this numerator, you will get this as one of the factors, right? I mean to say that, let me use some another page. It is b x square So you can have a b value such that if you just factor this polynomial, it turns out to be, this will turn out to be in this fashion: some x minus something, maybe some constant outside as well. And why am I want to do this factorization? Because if I calculate this, because I can always have such condition. Let's say, just look at the structure, just focus on the structure now. There is some number here and there is some number here, and you have this factorization. You can always do this, right? And just see, in the numerator, the degree of the polynomial is square. It's 2, right? So in the numerator also I should have degree 2, right? So this is consistent, so there is no ambiguity in that. But in the denominator you can write this as this. Now you can see that you have a common factor which was responsible for this to being a non-limiting value, I mean non-existing value. So just by doing this cancellation, now you can substitute. Now you can substitute your x equal to minus 2 in this case happily without any worry. So the idea is that you need to figure out what is that b, such that we have this kind of a factorization, so that you can solve this problem. So that's what the question number 24 tells you. So since they have asked this question, so I'll give you a hint. The hint is that yes, b exists, there exists, there exists such b such that limit exists. And I can tell you how to solve this problem. The first rule which I have, the trick which I have told you earlier, you can use this L'Hopital rule. Because since the limit is 0 by 0 form, right? So you can differentiate numerator and denominator, right? And this will still give you the answer. So my numerator was bx square plus 15x plus 15 plus b over x square plus x minus 2. Okay. And since you were asked to solve this, so just take a differentiation, right? And the numerator. So what you see here, you can see this is giving me 0 by 0 form. So you can just check by substituting. Because, I mean, just put the value here. To get this L'Hopital rule, you have 2bx plus 15, and you have 2x plus 1. Then you can substitute back to get your limiting value, which is 2b minus 2 plus 15, 2 plus 1. Now the answer is 15 minus 4b, 1 minus 4. But you just need the value of b, right? So how can you find the value of b? So the moment you know what is the value of b, you also know what is the value of limit. But since you can see that in this process I assumed my numerator turns out to be 0 when I substitute x equal to minus 2. So I will substitute that and check. I mean, I will impose that numerator is 0. If you guys have any problem, just ask me without any hesitation. So you can see now I have got an equation. I mean, the moment I solve, I'll get my answer, which is 4b plus 15 minus plus b minus 30 equal to 0. Now at the moment you solve them, it's 5b equal to 15, and b turns out to be 3. Now substitute this b here and you will get your final answer, which is 15 minus, yes, minus 3, which is 15 minus 12 over minus 3. You can see it's just minus 1. Hopefully this answers the question, right? Can I get a thumbs up so that I can understand people got what I have did here? I have tried to be little comprehensive here, but yeah. Can I get a thumbs up so that I can understand you guys got this question? So the answer for this question is turns out to be the b value is the b value was 3, right? Yeah, 3, and the limiting value was -1. So we have discussed this question. But I just guys, I want you guys to just try the 77th question because this is an interesting problem. Because this will teach you a lot of things. Okay? I'll go back to the 25th question in which we have to determine the value of a so that the function has a slant asymptote y equal to x plus 3. So this is again an interesting question in which I'll tell you the answer. The answer is a equal to 4. I have solved this question earlier as well. And it turns out that this function can be written as, I'll explain each and everything whatever I'm saying to you as this, because we just have to take the just division, right? Basic polynomial division. If you want to check whether this is right or wrong, just do a cross multiplication and check. If you're not convinced what I have did here, let me tell you what basically I have did. If you do this cross multiplication, right, you will see that this turns out to be and you can see here this will get cancelled with this. Here you have x squared plus ax plus 5 over x plus 1, which is the question, right? You can see from here, which is the question, exactly question. You can see from here as well. So what I have did is basically I've opened it. Okay, and the word you can see here, the word they have used, slant asymptote y equal to x plus 3. Basically, what does it trying to tell you that you have a function. This is very interesting question. I have picked this from a very good source. They have a very wonderful questions. The idea here is that you have a function f of x. You plot that function. Okay, you plot that function, and that function should make an asymptote with an equation y equal to x plus 3. You can see from here. Okay. So if I want to draw what is this y equal to x plus 3, which turns out to be this, and we have some red color function like drawn somewhere, um, and you want this function to make an asymptote with this. So if you try to plot this, we can see if you take x to the infinities, okay, yeah, I can see here, it will make some kind of a behavior like this. This is my f of x function, and this is my y equal to x plus 3. Okay. So what the question tells you that calculate the value of a, basically do the adjustments, do some adjustments in your function such that the function makes an asymptote with this particular line which is given to you in the problem, right? And the way it can make an asymptote, if I'm able to match this, right? Because that's what an asymptote is over here. You can see this is an asymptote. They are very close, but they never touch each other. So that's the story of an asymptote. You can say it's like a tangent and infinity, but that's just crude way of saying, but that's not exactly true. They are very close. I mean, you can say that when x tends to infinity, my basically f of x tends to x plus 3. That's what you can see from here. So that's what means by asymptotic behavior, or something called as an asymptote. So from this thing, now you can see that what this question basically trying to tell you. This question is basically trying to tell you that solve this limit such that this value tends to 3, right? For x goes to infinity. If my second part tends to 3 when x goes to infinity, so basically this will true, right? This will be true. So that's what this function is, this question is trying to tell you. Calculate the value of a such that my function behaves as y equal to x plus 3. Behave in the sense, in the asymptotic sense. Not everywhere, but in the asymptotic limit. You can see. I hope everyone is clear with this question. Can I get a thumbs up here? One thumbs up at least. Okay. So now we have this question that you have to solve x tends to infinity a minus 1 x plus 5 x plus 1 such that the answer comes out to be 3. And the way you can have the answer 3, if this coefficient which you see here is 3, right? Why am I saying that? Let me tell you. Because you can always write this question as this a minus s plus, I'll take a division by x on numerator and denominator. So what do I see here? Now if I take a limit, you can see that this whole particular thing will become 0 under the limit, right? So what are you left with? Now you're left with something called as a minus 1, and which you want it to be 3, and hence your a value is 4. And this is what I told you, that the answer is 4 in this case. Okay, so this is what I mean. Like, you can expect this kind of a design based questions, where no matter how much you try to solve question, but they will somehow design some interesting question like this, where the limits will be hidden inside. You can see how the limit is beautifully hidden over here, and you can also see from here as well how they have hide that limit things over here. So the next question is that you have to prove that function has horizontal asymptote, that is y equal to 0. That's what horizontal asymptote is, right? So here they have given you the function, okay, and they just want to calculate what's that horizontal asymptote. Basically it tells you that, just go to the new page and let me tell you that, let's say you have this function, and you can see here the value of the function is ln x over x of x equal to this, and you can see that the domain of function in this case, it's governed by two properties, one because of this, one because of this. Denominator tells you that x cannot be 0, and the numerator tells you that x has to greater than 0. So what do you see overall? The domain of the function is belongs to r plus, right? R plus, like positive real numbers. This is what the domain of the function is. So you understand now that I can shift this line here, because there is nothing exist on the negative part. Okay, and if you try to have a plot, if you see very carefully the plot for the log x, it turns out to be some, if you see the plot of the log x, turns out to be some this kind of a plot. Okay, so this is okay, okay. So this log x, and if you see the plot for the 1 over x, that turns out to be some this, maybe I have not drawn it perfectly. Okay, this is 1 over x, but now they have multiplied. So you can see you have something called a strange behavior here, and you can see that this point is actually 1 comma 0, where you have this particular thing. uh, it would be interesting to know what is that intersection point, but currently I'm not interested in that intersection point, but currently I'm interested in the behavior of this function. And because I'm trying to plot, make a plot out of it. So what do you see that in the case, see my ln x is positive, my ln x is positive for x greater than 1, my ln x is negative for x, you know, from 0 to 1. And if you see very carefully, my 1 over x is always positive for x greater than 0. So now you can understand how my original function going to behave like. So that turns out to be, the function will be 0. Let me add another color here. You have a 0 here. There is no question in that. And you have some large limit here. So this will behave as if this, and it will grow. I mean, you make a U-turn and just make a this kind of a thing. So this is how your f of x function going to look. You can check this on Desmos. There's a platform there. You can check them. So my idea is that you can see that blue point here, the blue line here. You can say this making some kind of an asymptote with the horizontal. So basically, over here I'm trying to explain you what is the question. Now, now we have to prove that function makes an asymptote. Mean to say that if I calculate my f of x as you can see asymptotes with the horizontal means this is what horizontal line is, right? Which has equation y equal to 0, right? Because in the x-axis all your y coordinates are 0, and this is making asymptote because your x moves faster compared to the log x. Your log x don't move faster. If you compare the x and the log x, see this is your x function, and this is how your log x behaves. I mean, yeah, you can just have a look. You can see log x moves rapidly compared to the ln x. So if you take a ratio, it is understandable, right, that overall the function going to approach to 0 as x tends to infinity. So this is what you have to prove. This is what you have to prove. This is what does it mean to say that it has an horizontal asymptote. Okay. Hopefully this answers your question. Now we will try to prove this. I have explained you what is the question. Now we will try to prove. Hopefully this answers your question. And over here we have this limit x tends to infinity, because we are interested in this asymptotic behavior, right? Asymptote behavior, where it matches, the behavior matches, like such that this function becomes like a horizontal line, like y equal to 0. That's what I mean to say. So ln x over x, and you can see that we have this infinity by infinity form. So in order to solve this, you can use L'Hopital rule. which basically tells you differentiate numerator and denominator both. So the moment you differentiate the numerator, you have 1 over x, and in the denominator you have 1. So overall you're left with just x tends to infinity, positive infinity, 1 over x, which is just 0, right? You can see from that green curve from here itself. From here I'm just trying to make you understand how to see things, okay? So we have basically proved proof. Okay, so that's what, and that's how we solve basically the question. So these two are done. I'll go with the 27th. 27th is an interesting problem because over here I have that I to be an open interval such that 4 belongs to that interval, and let the function be defined on a set D. Over here you can see in the D set, the difference between the D set and the I set is that in the D set you have removed the element 4. Why? Because I wanted to call this D set to be the domain of my function. Okay, and I is just an open interval as what they have basically wrote here. I is just an usual open interval. So better you guys understand what is the difference between D and I. I is some open interval in which 4 is included. But now in order to define my function, because of some reason, my function might not be defined at 4 because of some reason. I don't know. So, but I want to write down what is the domain of the function. So what I do, I remove this 4 in that interval I. And the way we remove that mathematically, we show that by using this backslash. Okay. So using this backslash, it means that you have removed an element from the set. And how do you see that that's an element? Because you have used a curly bracket, not an open bracket. So if you guys are still under in confusion, let me tell you, like for example, if you have an interval I and I want to remove another small interval, let's say some I prime. Let's say this was your interval I. Okay, and there exists a sub interval inside the I prime. So what I have did, I have removed this I prime from the I, and I denoted it as this using backslash and I prime, which I mean to say is this green color thing, right? What is this green color? This green color thing. So this is what your remaining set is. But over here in the problem, they have used this notation, this curly 4. Curly means discrete. Like they have exactly specified what they mean. Okay, otherwise they have used some other things. So this is all about the notation, definition, and all. So in the question, they want me to basically find the limiting value of the function at x equal to 4, where they have given that my function is always bounded between two given functions. So this immediately strikes you that it's better to use this bounds very carefully. Thing is that in this case, they have not given me the definition of function, what I do, but they have given me the most important information, which is very beautiful. Because now what you can use is something called as a sandwich theorem, which is my favorite theorem. And also because I like sandwiches. And the idea is that over here, since they have not given me a function, they just told me there is a function which has a domain some I backslash 4. That means 4 is removed just because a function is not well defined in this case. And we just want to figure out what is the limiting value. They want you to find this, which we don't know, but they have given me something interesting. And that something interesting is this. This basically tells you that my function is sandwiched between two different functions such that they follow this trend for all x belong to, for all x belongs to the domain of f. Hopefully everyone can see this what I'm trying to tell you here. Hopefully. Can I get a thumbs up so that I can understand everybody is getting the point? Okay. So in this case, that's good. Okay. So basically we have this function f of f. I don't know what is that function, but there is some function here, and we can see that. Okay, let me draw something realistic diagram, not something schematic. Um, okay. And the way I can draw my x plus 2 is this. Okay, this is my x plus 2 and my x square minus 10, which can be seen as this. So this is my x square and we have shifted it down like this. X square minus 10. I can do something interesting there. So this is your minus 10 here. Minus 10 in case you are wondering. And this is your 2. This is your x-axis. This is your y-axis. So now the interesting fact is, if in case wondering, this is my minus 2 and this is something called as root 10, I guess, and this is your minus root 10. I guess now I guess the situation is clear to all. Now what they did, they defined an interval in this such that the situation is okay. You can see the in the question you can see that over here my parabola is always greater than the function and my linear function is less than compared to both. So I'm just guessing what might be that interval, that interesting interval. That interesting interval might be this. Yeah, this maybe some like here, maybe this, in which the 4 is also included here. 4 and your function, your actual function might be running in this fashion. Uh, maybe some, I don't know, maybe some this way. Let's say. So you can see that in that given interval, now just focus yourself into this interval only. In this given interval. In this given interval, you can see that you have this kind of a behavior. Okay. So this is what graphically this might look to you. So what I basically did, I have zoomed this. But the interesting fact is not this. This is just have show you what is the situation. But the beautiful thing is that if my orange line, if my orange curve, for example, this, if I calculate my x tends to 4, x square minus 10, which turns out to be 16 minus 10, 4. And if I calculate the limit x tends to 4, oh, sorry, this is 6, sorry, I'm sorry. That's a 6. And if I calculate this, interestingly, they both have same limit. That means these two function touches. That means these two functions touches at some point. somewhere over here they are touching somewhere. So what you have, that you have this kind of a line, you have this line, and you have this original function here. So this is for fx, I mean some kind of a thing. Just for now, just go into the actual curve. Just get the idea what I'm trying to say here. We can say at over here they have a common value. At x equal to 4, if you try to calculate, the upper curve has limiting value 6 and the lower curve has limiting value also 6. But your situation was such that my function was always bounded between two. So you can see that my original function is get sandwiched between my two functions. So I'm guaranteed, since this is true, I'm guaranteed my limiting value of that function is also 6, because my function has to pass through that intersection. It's not actually intersection, but yeah, very close. Somehow we can call it as an intersection. So that's the idea. I hope you got this notion. Something called a sandwich theorem. Because your original function gets sandwiched between two known functions such that their limiting values are known at the same point, and it turns out to be same. So the function has to pass through that limiting value as well, because you want to hold this function, because you want to hold this definition, because this is true, because hold this, to hold this statement, because this was true, right, for all the values of the domain, the function. That was the idea here. So the answer turns out to be 6 in this case. So the answer is 6. Okay. Now we'll go to the 20th question, again, which is based on this particular concept which we discussed. I want you all guys to try this particular problem. I will write down the solution for this, and the solution turns out to be 1 in this case. Okay. You can check. You can orally do the solution. If you got the problem, previous problem, you can orally check this. Just substitute 1 over here, because this guy will tend to 1 and this guy will also tend to 1, as your x goes to 1. So the function also has to tend to 1 because of the sandwich theorem. That's it. That's what I'm trying to say here. Now we'll go to the next question. Okay, by the way, some books write the sandwich theorem as squeeze theorem. So they are same thing. They are not different. Okay. So they are also called as squeeze theorem. For example, the question from which I have taken, they have used the word something called as squeezed theorem. But they are same thing. The sandwich squeeze, same thing. But the question 29 basically tells you to find that functions so that you can apply, so that you can do that. I should write those, find those functions. Grammatically, this should be correct. Okay. So in the 29th question, you have to guess. In the case of 28 and 29, they have already told you what is that function here. You can see from here, right? If I remove this, you can see from here, they have already told you. They already given you those functions. This case also you can see the function is already given to you. Over here you can see, right? But in this question, you have to guess by yourself. You have to guess two functions such that your one function is greater than this, another function is less than this in the given interval, and such that both the functions have the same limiting value, which is 0. So that we can, without solving this, this is a very good theorem, right? Because solving this limit value is very difficult. It's better that I know some function which is easily solvable. In this case, you can see this is easily solvable, right? And just by solving them, I can know what is the limiting value of my function. Just because I know my function is bounded between these two known functions. So that's the idea here. And if in case you are wondering, uh, let me give you a quick solution, and I want you guys to check that. If you guys didn't get, we can discuss this in the next class. Uh, in this case, we will use the fact that sine of 1 over x, if you take the modulus of this, is always less than equal to 1. This is a very well known fact. Okay, I mean, for all x not equal to 0, for obviously, right? And we also know that we have this function e to the power x, which is increasing function. I mean, we have this function, right? This is also positive for all values of x belong to the real number. So what we can do, uh, what we can do here is that we can use this idea. Okay, I mean, for all x not equal to 0, why we are always writing this for all x not equal to 0? Because of this sine of 1 over x, because this makes uncomfortable to us. Okay, I'm basically trying to guess. How am I able to guess? How am I trying to guess this? Because I'm just looking the structure of this problem. What do I see here? Some exponentials, some sine of 1 over x. There is some factor related called as under root of x. So I'm basically trying to construct, using the similar pattern, similar structure that is already existing in this problem. So the first thing I saw this, and the second thing which I saw this exponential, right? So I'm just trying to make a conclusion out of these two statements, right? And the conclusion which I had here is this, which is true, right? No matter what x you take, except 0, this is always true, because my sign is oscillatory between minus and 1. So no matter what x value you put here, it will always be bounded between these two numbers. Okay. So now what if we multiply root x on everywhere? Why am I multiplying root x on everywhere without even have to worry about the sign of the inequalities? The reason is that because, let me just make a square here. No, let me shade this. I saw this, and I also saw something called as a root x, which is positive, right? For all x greater than 0. Yeah, let's use this color. So since my root x is a positive quantity, I can always multiply and divide by positive quantity throughout my inequality without have to worry about the sign, right? Because when you multiply a negative number in an equality, you have to worry about the sign. And now you can see I have constructed my function. You can see here. That's interesting, right? Let me use this color. This is what my function is. Exactly same function. So I constructed it such a way that I know what are those inequalities. And it turns out that uh, my root x, this function, my function is bounded e times of root x and root x over e. Now we just have to find out the limiting value. Now you just have to, in order to find this, Just prove this. They tends to 0, right? As x to tends 0. And you can see this also tends to 0 as x tends to 0 plus, right? So definitely hence proved. Okay. Now let's go to the next problem. I've given you the hint like how to solve. Not only hint, I basically solved the whole problem. But you might can also have other possibilities. It's just not that they are the only functions. They are not just the only. We can still construct many others. It's just your design thing. Okay. So this is how we can use the ideas. So in the question, everything is there already. We just need to use how and how to. I mean, to use it like yeah. I would not solve this problem now. If you have any question, any doubt, email me, text me, whatever. Just let me know if you're unable to solve this question. I will not solve this now. In the next session, I will solve if anyone couldn't able to solve this because this is very trivial. I'll consider this to be a very trivial problem. But don't hesitate. Text me. No issue. Now let's go to the 85th problem. This is an interesting problem because in this case, they tell you that you have to sketch an approximate function. Basically, sketch an approximate function. I mean, graph of a function. And in this graph, there are two points, P point and Q point. Okay. And when using the precise definition of limit, I mean to say this. Okay, this is too big. And a number delta and another epsilon are used. Show points on the graph which this evaluates, which this value determine. And recall that the interval determined by delta must not be greater than particular interval determined by epsilon. So basically in this problem they have told you to solve this particular problem using delta epsilon definitions, you can say notations. Okay. And in this case we have to find what is that interval like epsilon delta. Again I will not solve, this is very trivial. I will solve this in the next session. I will take these two questions in the next because they are very simple. I mean to do. A part I'm talking. For the B part, you can see using the graph to find the positive number delta. I guess this also follow up from the A part. If anyone has any doubt, please let me know. I can discuss it over here. If you want me to guys have this question in the next session, we can discuss in the next session as well. Okay, so let's go to the 86th question. So this question basically tells you that if my f dash is continuous, using L'Hospital rule to show that this is true. Now basically you have to prove this, that this is true. If you see very carefully, this is basically my definition of derivatives. Just instead of, you know, defining an interval this way, such that you earlier cases you had this kind of a business in which you had this x fx and you had this x plus h f of x plus h. You basically took the step size or the interval to be h. Now what you're doing, you're doing something interesting, and the interesting fact is that this whole thing is equivalent. This whole business is equivalent to what I will tell you now. You can also do this. In which you have a function and you are basically trying to calculate uh, f dash of x at this particular position. Okay, so what do, we first go to this point which is h distance away, and that point is basically x minus h, f of x minus h. Then you take another point, this, which is also h distance away from this x. So this is your x, and let's say this is your x, this is your x plus h, x minus h, and in this case it is x plus h, f of x plus h. In the previous case, you were defining this, the difference in y or difference in h, right? And you are solving this limit to say that this is my definition of limit, the original case. But here also we'll do the same, right? Because here you can see you have some triangle, right? And this triangle is, you can understand, it's very small, very small triangle. And over here also, if you want to calculate the slope, because the slope of this particular hypotenuse, the slope of this hypotenuse is approximately same as what you see that instantaneous slope at that x, right? I mean, this red line is basically the tangent at that particular point, and that is what basically calculates this, right? So my claim is that they are same, more or less they are same, and that's what the definition is. And the same trick you will do, you will just take the difference of the numerator and the denominator. So this is the difference on the numerator, this is the difference in the denominator, which turns out to be 2h, and you will take h to 0, and this will basically tells you the same idea. That's it. That's what the problem is, and that's what it is trying to tell you. Exact same thing, right? And if you're not still convinced, like what we have did here, we can refer this diagram here. Just refer this diagram, like what we have did. This explains what you have done. And you can see in the diagram, I mean the question also, you can see they have told to explain this. In the question you can see, explain the meaning of this equation with the aid of the diagram. So that's what actually I have did here. I drew the diagram and told you that yeah, this is how we did. And let's go to the next problem. The next problem deals with the continuity. So far we have solved this many questions. The next question we will see, like we know the function is defined to us. It has two branches, and the first part tells you to calculate what is the value of the function, what is the value of the constant c, so that the function is continuous. And we know the definition of the continuity is that the function left hand limit and the right hand limit is also equal to the value of that function. Okay, and if you see very carefully here, my f of x function is defined in c minus x. I would encourage you to draw a plot for these functions when you're done with the when you're done with the solving. Okay, let's say you got this problem and you solved this algebraically, right? Because this basically tells you, I mean, the question don't want you to draw a graph unless this explicitly write this. You don't have to draw a graph because the tools which we are using is an algebraic tool. Okay, but I would encourage, whatever the question is at the end, try to make a graph of it, because this will help you to see things. Okay, Uh, okay, so we have c minus x and c sine x. If x less than equal to pi, and if x is greater than equal to the pi. Now the way we can solve that, first we will calculate what is the value of function at pi, and we will use this above definition, because this is where my x is equal to pi, because this branch contains x equal to pi, not this branch contains, and we will calculate. The answer comes out to be c minus pi. Okay. But we have to calculate what is something called as a left hand limit, because at the end we will use the idea that my function is continuous, right? So my left hand limit would be limit x tends to pi minus and f of x. But we know for the pi minus my definitions are defined. Okay, okay, there is a problem here. That's it. Yeah. So we will use this definition, which turns out to be limit x tends to pi minus, and that is actually c minus x. But since we can substitute this over here, because there is no indeterminate form here, we can just directly go and substitute, and that turns out to be c minus pi. But if we check the right hand limit, which is x tends to pi plus, we are approaching from the right, so that turns out to be limit x tends to pi plus, and we will use this definition. In case you guys are wondering, I'll mark them. And this turns out to be c sine x. And since again this is not a indeterminate form, you can directly go and substitute, and that turns out to be c times 0, which is 0. But okay, I use f of x is continuous, implies my right hand limit should be equal to the left hand limit, implies 0 should be equal to the c minus pi, imply my c is pi. That's how we solve this continuity problem. Okay, and the next part, they have asked me to find the value of c. I mean, the value of c found above, verify that whether three conditions for continuity are satisfied. Yes, three conditions, they mean to say that continuity, the three conditions are that, first of all, my function is defined at x equal to pi. Yes, it is defined. Second, left hand limit is equal to the right hand limit. Yes, it is true. So my left hand limit, right hand limit, is this equal to the f of a? Yeah, this is also true. So it basically satisfies all three conditions. So my b part get verified, right? Because that's what the conditions are to say that my functions is continuous at that particular time. So that's what my b point is. And c point just basically tells you to calculate the graph. So the graph turns out to be, since I know uh, this will be pi minus x, so that means we have this particular line, and the difference comes here. This is your line with your pi minus x. Why am I saying that this is my pi minus x? Because if you take the extension, it will touch at pi, and you can see the slope is also negative. And yes, do you have any question? And you can see here now the next part is pi sine x. because my function has two parts. That is the pi minus x, another was pi sine x for x greater than equal to pi or x less than pi. So I plotted this happily. Uh, to avoid confusion, this is not the actual point. And you can see this is an oscillatory function with an amplitude of pi. And here you have this pi comma 0. And we know sine makes this kind of a curve, right? And you can just go on doing this. So this basically solves problem. So this is your pi sine x part, and this is your x pi minus x, and this is where you have this continuity. The question was asked. This is your 0, right? And you can see this is what my pi. And if you just try to make an extension of this, you can see that touches, right? So this is what the situation is. So this is what I mean to say draw, right? This is what it means to say draw a graph. Okay, so now you have complete picture. What is happening here? Till x equal to pi, I had this oscillatory behavior. Oscillatory in the sense sinusoidal, sine, cosine, which oscillates between 0 and 1. But since we have multiplied it by a number pi, so you can see that now the amplitude of oscillations are pi in this case. And from here, it behaves as a linear function. So that's what is mean. So this question is done. I'll go to the next question. That is basically use the intermediate value property to show that this for some x greater than 0. I have to show this. I have to prove this using the intermediate value property. I hope everybody understand what is this intermediate value property. Let me note down. We can consider this function fx. Let me just make a line here. They are different things. This is what we want to prove. And we see that the domain of the function in this case is real number except at 0, right? Because we just discussed what do we mean by the subtraction and the backslash over here. And that on this domain as a sum of two continuous function. So you can say there are two continuous functions, right, involved here. This is a continuous function and this is another continuous function. In case you were wondering, yeah. Both the functions are continuous, so my overall function is also continuous since my both functions are continuous. And since f is continuous on 0 to infinity, and since my limit x tends to 0 plus is minus infinity, you can check this, right? If I calculate x tends to 0 plus for this function, it turns out to be minus infinity. And if I try to calculate this x tends to infinity, I see that my function goes to infinity as well. How do I see that? You can see this because of this, because this is the leading behavior when x goes to infinity, and this what behaves this, because when x tends to 0 plus, you see the second terms dominate over the first term, right? So we are basically have two powers which are trying to dominate each other. Depending on their values, they behave such a way. So the typical graph, what I can see here, the typical graph But I can see here for the 0. Okay, so let me do this. Hmm. This is x, this is some function f of x, and I just immediately saw that the asymptotic behavior of the function, asymptotic behavior in the sense that when x goes to infinity, my function also goes to infinity because of this exponential, right? So when x goes to infinity, my overall function can be approximated as 2 to the power x. But when x goes to 0 plus, my function can be approximated as minus 10 over x. So you can see like how we construct this particular problem. And I just wanted to know what is the value of x for such that the function is 0, because okay, uh, so you can see that I have this blue line here and some this line here. And the important point is, since my f of x is continuous for all x greater than 0, now I will using IV intermediate value theorem, IVT. I can say intermediate value. I guess in this question paper they have told it's intermediate value property. Okay, IV property. There exists a such that my f of a is 0, right? Because if my function is continuous, I know it behaves in this fashion. I know this limiting behavior. That means somehow in between there's something happening, right? You might have this possibilities, you might have this possibility, or you might have another possibility, for example this, or you might have something very crazy, for example crazy in the sense, you might have this kind of thing, right? But thing is that you have to cross the x-axis at least once to do this, right? Like this is confirmed, this is no ambiguity in this, no ambiguity in this. But maybe in center, I don't know what is happening, but I'm sure that my function is continuous, right? My function is continuous. I just checked, right? That's why I wrote everything here. That means using my intermediate value property, I can say that there exists a, right? There exists a solution in the sense that there exists a value of x for which my function is 0, right? So that means I have just proved it, right? The statement, because they have asked me to prove for some for some, right? For some value, and I just told you this. There exists some value using this intermediate value theorem. Because my intermediate value theorem, if you recall, in case you have might forgotten, show you over here. Uh, Somewhere here I remember. Maybe not in this notes. Okay, not in over here. It's somewhere in my old lectures. You can see. The idea is that whenever you have this 2 point A and B, in which is multiply and it turns out to be negative, that means there exists a point. For example, there exists a point C such that my f of C is 0, because over here it is my f of A and here is my f of B. That's what my IVT. Okay. That's what I have used here to prove this second part. So this question is done. Third question is very simple. I want you guys to try this. If anyone of you are unable to do this, we can discuss this in the next session. Okay? This is very simple. Just play. I mean, this is a true or false statement. Just play with. And if you can get an expert enough so that you can solve this question by verbally. Like, for example, in the first case, they ask you, is function continuous at x equal to 1? So you need to see where is my x equal to 1 behavior is. So you can see here, my x equal to 1 is over here. So just focus here. For this problem, just focus here. Focus here. Because at x equal to 1, my function is defined as 5 by 2. But if I calculate what is my left hand limit, yeah, that's false. Exactly. Exactly. So the idea is that you can solve this. So I'm basically trying to explain the others who couldn't able to do this. So anyways, I'll discuss this in the next session. I'll go to the next interesting question, which is this. In this case, we will assume there is a function. By the way, you will find all these questions in my Google Drive, which I have already shared with you. I have uploaded the whole set of questions you can see here. I mean, it's a big set of questions. We'll discuss all of them. I have interesting questions. It's very hard to find this interesting question anywhere. You can see we'll discuss some good features and good maths. I will also upload some casual videos in the YouTube so that you can watch them later. Not necessarily on the Monday. For example, if I get some time somewhere in the week, I'll upload some few solution videos, okay, so that you can see them. Or just text me. I'll make a solution video for that. I'll include those questions in that solution video, and I'll upload it. So in this case, we have to assume there is a function. It has two branches, and the problem is at the x equal to 1. So we have to determine whether the function is continuous at x equal to 1 and justify your answer and state your conclusion. Exactly, just do your analysis. First calculate what is my left hand limit, just calculate what is my right hand limit, and see what is my f of 1. Okay, and then just check what is the value. By just by looking, I can say that my left hand limit is because of this part, and if you put x equal to 1 here, you will be having 6 by 2, which is 3. Okay, and your right hand limit is because of this, and if you put 1, which comes out to be 3, and if you calculate what is my f of 1, which is over here, which turns out to be again 3. So in this case, left hand limit, right hand limit, and your function value is same. So what do we conclude? Function is continuous. And here is my justification, you can say. Okay, just have used the definitions of continuity. So using the definition, the derivative determine f dash 1. This is interesting. This is absolutely interesting. By looking to the problem, I can immediately say the function, the derivative at x equal to 1 do not exist. I can immediately say this. Immediately. Basically, this is what they are trying to say, whether, determine in the sense, figure out what is the value. So first, before you determine the value, you first check whether this limit exists or not, right? And the way you can do this, just take a derivative, right? Just calculate derivative, and turns out to be the derivative takes this form. Interestingly, at x equal to 1, my right hand derivative is half, but left hand derivative is also half. That's interesting, right? And if you calculate what is my f dash 1, that is also half. So this case, you are very lucky. In this case, you are very lucky. Sense that not only the limit exists, but it has a value, and that comes out to be half. The problem comes when there was some other value other than 1. For example, let's say you might have a function which is defined in this way, in which the ambiguity is in this. Let's say there was some 5, not this. What is this? Instead of 1, there was 5. In this case, you might not have access to this value, right? Coincidentally, my derivatives of this and this matches at x equal to 1. But you have to be careful, right? Sometimes you can just by looking, you can see the answer. So this is also done. And in the fifth question, it basically tells you give one example of a function that is continuous for all values of x except x equal to 3, where it has a removable discontinuity, and explain how you know that function is discontinuous at x equal to 3, and how you know that the discontinuity is removable. In the first class itself, I told you, not in the first class, maybe in the later class, uh, whenever you have a function like this, and let's say, yeah, exactly, this is also one of the example. Yeah, that's true. Whenever you have this kind of a situation, you can see over here the derivative. I mean, the function is not continuous in this case. You can see there is a jump here, discontinuous jumps. So this kind of a discontinuous jump is what we call as a removable discontinuity. So if we have a problem like this, if we were able to construct a problem like this, you have basically a removable discontinuity. I can remove this discontinuity just by doing one simple step, that is to redefine your problem, redefine your function such that this problem you have to fix over here. That's it. Just bring it back to where it should be, basically, so that you have a smooth line. So since this is an open problem, we can have thousands of examples. So I will let you guys to solve this problem. Okay. And 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 please don't construct a function in which you don't have a definition at x equal to 3. For example, this kind of a function. This is not a valid function because you have a irremovable discontinuity. Why? Because now at x equal to 3, you have something called as this. Uh, right? Let's say this is 1 over x minus 3. We can say definitely I do have something called as discontinuity here, but that's not a removable. You can see. And obviously left hand limit and right hand limit also do not approach to some direction. I mean, this is not a definitely an example. So avoid this. They are not. Now we'll go back to the problem set. This are something called a miscellaneous problem, where a miscellaneous approaches would be used, not just single approach. Miscellaneous in the sense like all concepts are mixed up together so that you can solve them and understand which concept should be used at which time. So the first problem is basically to solve the following equation. This is an interesting problem. How will you solve this? That is an interesting problem. How will you solve this? That is also an interesting problem. And the second question they ask, find the domain of the function. Yes, you were saying something in on both sides. So what do you mean by in on both sides? You can open up your mic, there's no issue in there. Yeah, this is basically take a natural log. Exactly, take a natural log on both sides, so you will get a smooth function. And you can basically define this, you can take a natural log such that we have x plus 1 log pi equal to 1, and you can define a function like this, f of x such that x plus, you know, some, it just basically becomes this, uh, you can see here you have basically a constant line which is y equal to 1, and we have another line which has a intercept something called as log pi. I'm sure like this should pass here, and I should have slope like this. So over here you have this intersection, here you have the solution. I mean, I'm just showing you graphically, so there are graphical methods, but I'll skip this so that you guys can solve. If anyone couldn't solve this, we can discuss this next time because this is a very trivial problem. So my next question is to find this, the domain of the function. And you can see here the domain is because of various reasons. You have to go from outside to the inside so that you can solve the problem. First, you need to see that because of the denominator, your x cannot be 3, and because of the numerator, you can see from here, right? Your your ln of ln x has to be positive because my numerator has something called as ln of something, right? And that ln of something has to be positive because ln is just natural log. And what you see here, and the way it can be positive if my ln x is greater than 1, because we just saw the plot of this uh, ln function, right? I just told you this. So this is what we're basically trying to use here. This exactly. And over here you see now your x should be greater than e. So the domain of the function turns out to be, and you have to just see whether e is greater than 3 or not. So what I see here that my value of my domain of the function is e to 3 open interval union 3 to infinity. Right? This is one of the way you can eliminate 3 in your interval, or otherwise you can write down in this way, e to infinity minus by doing this backslash 3, or you can say, or always of doing the thing. So both are fine. This is also fine, this is also fine. So you might see anything in the option, so you have to just check. So you can see over here we don't have any problem of domain because over here is real to real, like minus infinity to infinity. Over here we had the problem we just saw, and such that all should be defined well, we have to take an intersection of all, right? So that's what we did here. Now let's go to the next problem. So I just write down the answer here, e to infinity backslash, that's it. So this is done. I want you guys to solve this problem. And there's a third question. So what it's meant by saying that L is the limit of a function as x approaches to where? See, that is the definition. So this can be seen as, you know, redefine this, say this using intervals. When I say that fx approaches L, I mean to say L is the limit. In fx limit is L as x approaches to A. So you define this by using that, write down the intervals and the definition which you have. That is for all epsilon greater than 0, there exists delta greater than 0 such that my f of x minus L, the distance between them, is less than the interval. So this is what I mean to say, limit for all x approaches to 0 means there is a neighborhood and interval around the A. I mean to say this. Sorry, this. So this is what I mean. Which I have wrote in this red color. Okay. So yeah, that's it. I mean, that's the better way to say that. So what is meant by saying that the function is continuous at x equal to a? Continuous x equal to in the sense that first, if the limit value exists, if my A statement is true, along with the fact that my function is defined at x equal to a, and that defined value is also equal to the limit value, then I say that my function is continuous. So that's what I mean to say that my function is continuous at x equal to a. I hope this clarifies, but I'll still write down for few. It's okay to write down things. So this means that limit exists, and okay, the first thing, and the second thing, function is defined, and the third thing,
at f of
this is just, yeah, f of,
a.
yeah, exactly, yeah, the limit exists and also equal to the f of a. I mean to say the limiting value, you can write this way, like limiting value is equal to the value, functional value, function value at whatever the point is. I mean at a, yeah, I'm just trying to write down in an English, just avoiding mathematics, I mean language. In the math language I would just write this, limit x tends to a, f of a equal to L, and I would say, yeah, you know a, it contains, I mean a is contained in the domain of f. Yeah, a is contained in the domain of f. A is a subset, I mean a is a part of the domain. So this is what says, right? I hope this is clear to all, like this particular part, I guess. This means a is contained inside the domain. The say, I mean to say that
Yes.
at a we have the definition. That's what I mean. And the C part basically tells you that state two properties that a continuous function can have, either of which guarantee that the function is not differentiable at x equal to a. So there are two properties that a continuous function have, but that is not guaranteed in the case of differentiability language. Can you guess what is that? Or do you want to try this and want me to answer in the next time? This is simple.
Yes, this one I didn't get.
Yes.
This question I don't know, sir. Actually.
Yeah, you can try. I mean to say you can try. Next time we'll discuss this. I will discuss all the circle points. I mean to say.
Yes.
Next time I'll just. I think so. It got hanged over. I think so. This is my 1 minute. Somehow I'm unable to change the page. Okay. So this was the page. Okay, now I can change. So basically, what I was trying to say, that I will discuss all the circle points because I want you guys to have a give a try. I mean, just give a try to this. I'll come back to all the circle points. I'll revise starting with the circles.
Okay,
There
sir.
are few properties which are true in the case of continuous functions, but they are not true in the case of the differential methods. I mean, at x equal to a. So just check them, and you can illustrate that with a diagram. Now let's go to the 22 part, derivatives. So in the case of derivatives, the first question basically asks that we have to assume a function, a real valued function defined for all values of x on an open interval whose center is a certain real number a. So what does it mean to say that function has derivative at x equal to a? So this is what uh, it's just basically trying to tell you. Uh, so you have to just give the definition. I mean, you know the epsilon delta definition which we have talked earlier. So just write down the definition in this case. I mean nothing interesting. I mean to say, just write down the definition. You know that definition which we have discussed earlier. In case if you are unable to recall, this. Oh sorry, there's a problem here. They have asked in the terms of a, not in terms of h. A, a. So using the definition of f dash a, you have just given a part A. I mean a part A में जो हमने like whatever the we did in the part A. So using that definition we have to prove this. Let me do this for you for at least once. Like how we can properly write down everything. So in this case we have this f dash 3 would be limit h tend to 0. This was my function, right? You can see from here, right? My function is 1 over 2x minus 1. In case this was my function, okay? So I'm basically calculating my this value 3 plus h, which is just would be 2 times of 3 plus h minus 1. That's it. And I'll take a difference with f of 3, which is just 6 minus 1, which is 1 over 5, right? Over h. And you can see that immediately this comes out around minus 0.08. So this is what actually the question was asked to calculate, nothing more. And in the C part, they've again asked you to calculate this. And over here, you can see that this is something strange. Strange in the sense by just by looking, I cannot say what is the function here. I mean, this doesn't look like we are trying to solve some, we are trying to apply some definition of derivative, right? Because I'm unable to find this kind of a structure here. I can see there's a function involved here, but the same function doesn't look same here, right?
So that half we can consider sine pi by 6.
Sine pi by 6. Yeah, that's true. So yeah, you actually have already the answer. I mean, I was approaching that particular answer, but in a build up way. So you already know the answer. Yeah, that's true. Here the function is basically sine of x, and here we are basically trying to calculate f dash pi by 6. That's it. So I guess power 7. Yeah, sine to the power 7 is limit x tends to pi by 6. Over here you have this sine to the power 7 pi by 6 plus h by 2 here, I guess. They have taken h by 2, right? Oh, I can do this as well, right? I can multiply and divide by 2.
Yes.
Yeah, what I'll do that. Definitely there is h by 2 here. Do this sine of pi by 6, 7. There is h, right? And multiply by 2 and divide by 2. Earlier there was not there. Now you can see I have a definition of derivative. So better I do this twice of this. Yeah, that's it. And you can just replace h with some. Oh, sorry, I have another. I again I have made a mistake here. There is some h by 2 goes to 0. Same thing. So over here I was just trying to tell you how to look, how to see. Exactly. So let's go to the next part. So the next question we see that let I be the bounded function on R and define f by this. So I is some bounded function. I don't know what is that function, but I is bounded. That means I can always, since you they have used the word called as bounded, that means there exists a capital M greater than 0 such that my mod of I of x is always less than equal to M. Let's go and say strict, right? Let's go and strict. Let's take a very strict condition like this. For all x belong to the domain of I. Are you familiar with this? Are you comfortable with this? What I have wrote here?
So the mathematical terms used, I'm not familiar with it.
Okay, okay. That's good. You have spoken up. That's really good. Because I don't know, you might be able to see such questions in the question paper. I don't know, but you definitely will see such things. That's why.
Yes.
So the idea is that this symbol means there exists. Is this clear to you?
Yes, sir.
Literal English meaning there exist. Okay. This symbol basically tells you such that shortcut, basically short way to write now, such that,
Yes, sir.
and this basically tells you for all. So what I have basically
Yes, sir.
wrote is as an English statement, but in a fancy way, nothing more. So the idea is that let's say you have this function here, some this function here, this let's say this is some I of x. You can see that my this function is bounded. Bounded in the sense that there exist two horizontal line. There exists two horizontal line, and inside that horizontal line, my function is bounded. Did you get this point?
Yes, sir. It cannot go either up or down.
Yeah, it is bounded between these two horizontal lines. It's like confined, right? I can always
Yes.
find this two, right? And surprisingly, this y is equal to m, and this y equal to minus m. I can always find. What I'll do, I basically get what is the maximum value of the function which can take, irrespective of sign, like maximum distance from the 0, like vertical distance.
Yes, sir.
What I'll do, I'll find that maximum vertical distance. For example, let that vertical distance comes out to be, let's say 5.6, right? Then what I'll do, I'll basically construct, I will construct two horizontal line I say that there exists two horizontal lines such that y equal to 6 and y equal to minus 6, such that my function is always, you know, between these two horizontal lines, right? So I can say that 6 is my m, right?
So m always needs to be an integer.
Yeah, yeah. Can you repeat?
M always needs to be an integer.
Yeah, it can be anything. It can be anything. Anything. M can be integer. Anything. See here, over here, I have not wrote anything like m has to be integer. I said m is greater than 0, a positive number,
Yes,
right? And how can you see the two
yes,
horizontal line over here? See over here, you can see two horizontal lines. Can you see? Or should I elaborate more?
yes,
See, there's a modulus, right? Outside. If you open the modulus, it opens as a plus and minus, right? So what do you see?
yes, sir.
You see there's I of x is equal to plus or minus n, right? Okay. So you can see like what do you see here? Like no, not this way, sorry, not this way. Your mod of I of x, which was written like this, will actually get open like this. So you can see, right?
It is bounded
Two
with the
horizontal
minus.
lines here. Your function is inside this two horizontal lines. So that means, so whenever I say, I mean to say I'm bounded, so that means I can always have this two horizontal lines. I can always find such two horizontal lines such that my function is inside this two horizontal lines. So whenever I can do this, I say that my function is bounded. Now do you understand the things which I have written on up?
Yes, sir. Understood.
Okay, so this means for all values of x, right? Whatever the function takes. Okay, so that's what
Okay.
this means. So this is what actually I mean to say over here. So better I erase this so that uh, so m can be anything unless and until I write m is an integer, that can be anything. And the reason I have took
So
here the pause. Yes, yes.
the value of m, the upper line, is always equal to the value of m lower line, or there it need not be so.
No, see, in general, see, if I talk about in general, the both horizontal line might have a different magnitude. For example, maybe not
Yes,
plus
sir.
m minus n, but what I'll do, I'll basically take the maximum of them, right? And again, I can construct, for
Yes,
example, let me give you an example. This will clear your doubt. Let's say my function was defined in this way. Okay, I can clearly see this is a bounded function. I can clearly see
yes,
because I can construct two horizontal lines. This and let's say this, and inside these two horizontal lines, my function is confined, right? Let's say this might be your y equal to minus 1, and let's say this is your y equal to 7, for example. You can say they are different, right? They are different.
yes, yes,
But how do I write in this language? So you know what this language tells you? You just take the maximum of them. Maximum in the sense, in the terms of magnitude. Do you understand the word magnitude? I mean,
yes, sir.
okay. So
Right.
in the terms of magnitude, this is greater, right? 7 is larger. So instead of creating this my horizontal line, I'll create this as a horizontal line, right? Still it is true, right? Still all the things true.
Yes, sir.
I cannot have this as line. I cannot have this as my horizontal line, right? Are you sure, right? Why this is not? This is true. This
Yes,
is
sir.
true. So the idea is that
Yep.
instead of writing y equal to minus 1, I would prefer to write as y equal to minus 7, so that I have to use only one thing, right? Otherwise,
Very.
I have to use two different things, right? For example, the other way, the original way, which I wrote it in the earlier case, the original way can be written as this way. There exists small m greater than 0, capital M greater than, no, there exists, mm, huh, there exists small m comma capital M belong to real number. Are you familiar with this notations?
Yes, sir.
So there exists small m, capital M belonging to the real number such that small m is less than f of x and f of x is less than capital M for all x belonging to the domain of f. Is this clear what I have written here?
Yes, sir.
Clear, right? This is your lower horizontal and this is your upper horizontal line. In this case, you can see they are not the same magnitude. They don't have same magnitude. So instead of writing this way, what I could have done, I would have taken the maximum of both, right? For example, let's say this, tilde, curly m, let's say this curly m. So I would have written this, right? There exists curly m greater than 0 such that my mod of fx is less than curly m for all x belonging to definition of f. Are you able to understand they are both are same statement? They are not different.
Yes, sir.
So that's the idea what I have used here. Nothing crazy. That's good. That's good. You have opened up and asked because that's a really good sign. And so in this case, they have given me a function in which now let's go to a main question in which I have two parts, x square and I of x, and this is bounded. Okay, and we have to show that my function is differentiable at x equal to 0. This is very interesting. It's really interesting because you might have continuity at a given point, but you might not have a differentiability at a given point, right? I can give you one good example. For example, this function is continuous at x equal to 0. This function is not differentiable at x equal to 0. Do you understand why is
Yes.
that true? It's clear, right?
Yes, sir.
So I can make that continuous, by doing something interesting. And that interesting thing is by multiplying it by x. That might solve my problem.
Yes, sir.
You can see that this will open up as my x square minus x square. Can I do something better? Hmm. Yeah. What if I put a minus outside? Yeah, that's true. Yeah, if I just multiply, my idea is that you can always multiply a factor, pre-factors, which will, which will do some regular changes, which is required to make that differentiable. Uh, Maybe we can do this. Yeah, this will work. In this case, you can see I have multiplied this required factor here. Now, what this will do, this will make this, and if you try to try to plot, have a graph, perfectly continuous and differentiable, like exact parabola, which you had earlier. So you can see a small factor, pre-factor, fixes the problem over here.
Yes, sir.
So you have to show that why this function is differentiable. So how can you show that? By using the definition. That's it. I can show you in this sense. See my f dash. See over here in the question they have asked for all, right? Oh, at x equal to 0. Okay, that's good. Only at x equal to 0. It means this can be written as fh f0h, and that would be limit h tends to 0, h square I of h minus 0 over h. So what do you see? H times I of h And since in the question they have told you this is bounded, so what does it mean? That this guy has some finite value, right?
Yes, sir.
But you see that on the right hand side you have something called as which approaches to zero. So zero into finite value is some zero, right?
Yes, sir.
So what do you see that f dash zero is zero and it exists, and the answer is zero. I guess that's what they have asked to prove, right? If I'm not wrong. Yeah, I just showed that
Ye-
differentiable. That's it. Yeah, you can see from that how we have proved. I'm just erasing. Okay,
Yes.
let's go to the next question. We will we will sit down for more 5 minutes. Then we'll close up this session. Mm, using the definition of derivative, we have to find what is this particular value. That is the derivative at 2. The function is given to us, and that's very interesting function. I can tell you the what is the plot of this function. This function plot has this particular feature. Yeah, exactly. This makes an asymptote at y equal to x, and the plot turns out to be this. This is interesting, right? And this minima happens. This minima is at x equal to 1, and in the answer you get 2. So this is what your function is. X plus 1 over x. This function exactly. So they just want to understand what is the derivative at some over here. Let's say at x equal to 2, and what is the slope. And I'm expecting that the slope will be very close to 1, because we can see the asymptotic behavior, how that function matches with the y equal to x. I'm not saying it is equal to 1, so I'm saying it's very close to 1. So that's what I'm expecting. And if you take a derivative over here, it turns out to be 1 plus 1 over x square. And if I substitute, it is this. It turns out to be 3 by 4, which is 0.75. Okay, maybe you have to go further more on the right. For example, x equal to 10 or 5. Then you can see it's very close to 1. But over here, we have to use the definition. That means you have to use this particular formula. So I can show you that. F dash 2 oh, again and again I make the same mistake. Actually, by the way, there is another way to write down the same derivative statement. Um, the way is this: f of x minus f of a, x minus a, limit x tends to a. This is also a definition of this. You can note down somewhere, and you can check. This works very good. Actually, I'm used to of this definition.
Yes.
Yeah, but thing is that you can find this somewhere, so don't get surprised. Thing is that you can define as much as you like, as the way you like. The thing is that the limiting behavior should be same. You have to just rearrange your intervals. That's it. I mean, everything would be same. So in this case, you have 2 plus h minus 2 plus 1 over 2 over h, and limit h tends to 0. And I'll just take the limit and you will find. And I'm sure this will come out to be 0.75. I'm sure. Just go through it. You will understand what happens here, because we can immediately see from here. Let me go through more. You can immediately see that, this two will get cancelled. We have this h minus 2 plus h minus 1 over 2, and overall you have 1 over h outside. So this h will multiply by over here. This will h also gets multiplied over here. But when this h multiplied in third term, this will limit to 0. So only first two term will survive. So you can say that you have just 1 plus and some, no, sorry, 1 minus h over 2 plus h. So from here you can see how value will transform. If g, now let's go to the third question. This is done. This is done. And the fourth question, if g is continuous but not differentiable at x equal to 0, okay, these are the initial conditions. Sometimes we call this as initial conditions. You will understand why later on. And f of x and g of x are related in such a way. Then we have to find f dash 0. So I think so we have to use definition. I don't know, like, let's do it in general. Just take derivative on both sides. You have this, apply the product rule. You have this plus x times of g dash of x, and just,
G dash of x.
yeah, exactly, just substitute 0.
8.
You have g of 0, that's it. And so f dash of 0 is just g of 0, that is 8. That's it. So this is without using definition, but I guess they have designed this question such that you use the definition and try to construct that g prime of x. Maybe, I mean, they might you to see this. Check out. Again, we will come back to this question again the next time. Just see that we have got the correct way or not. So state the definition of the derivative. I mean, again, you guys can do this. Same thing. Let's go to the sixth question. I'm erasing this, okay? Today
Yes, sir.
itself, I upload this video in the YouTube so that you can refer back whenever you want. So let f be the function such that the continuous everywhere, and let what? Let use the definition of derivative to evaluate. Okay, so you have to evaluate this using definition. It's easy, right? I mean, at 0, right? Okay. Okay, so you have to keep the answers in the terms of f. Okay. So you have this h sine square h over h minus, say, 0, because that's what the definition is, right? See here. And in the denominator we have this h, and you can see here, this would be, okay, so they have told the function is continuous everywhere. That's good, because it's a good sign. If it's continuous everywhere, that means that is bounded. That's true. If function is continuous everywhere, that means it is bounded. So this means that my f of x is bounded, and we will use that extensively, that f of h sine square h over h square. This whole thing will tend to 1. So you have basically f of 0. I guess this is simple, right? Nothing complicated. Everybody knows that sine h over h would be tends to 1, right?
Yes, sir.
So over here we have the function is continuous and differentiable at x equal to 1. Find the values for the constant m and b. So we have to look for a constant value of m and b such that it is continuous and differentiable. See, if you have solved for the differentiable, you don't have to solve for the continuous. If a function is differentiable, then definitely that's continuous, right?
Continuous. Yes, sir.
So I'll go for the bigger part. I mean, I'll go for the bigger fish. That is, I'll go and take a derivative. This will be this. This will be m. This is for x less than equal to 1, and this is for x greater than 1. And since this has to be differentiable, that means this f dash x has to be continuous, right? That means my e to the power 1 has to be m, right? That
And
my
b is
m
0.
is values, that my m value is e.
Yes, sir.
So from here I know that m value is e. But we can see that using this process I cannot know what is the value of b. So I have to do this particular thing,
30.
continuity. Yeah, exactly. We have to check this. This will give me the value of b. Many
B is
times
0.
what happens, problems get solved immediately just by doing this. But in this case, they have formulated the problem such that you have to also use this to get the value of b. I hope the answer is clear, right? Okay. From looking from here, I can say that the answer is b equal to 0. Yeah, you can see. B equal to 0 will work because my m is e and I'm checking at x equal to 1. So b has to be 0. So that my function is continuous smooth line at x equal to 1. So let me write down answer. Over here my m is e and b is 0. And my eighth question tells you that suppose the function fx and g of x satisfy the following properties. So you have to basically simplify your answer. Simplify in the sense if this is true, you have to find this prime. Basically, you have to prime this h dash 3. Okay. For now, I will just solve this problem. Then we'll close the session. Okay. Since we have to solve this, that means we have to solve. Okay. First, we see that f dash of x is basically g of x f dash of x minus f of x g dash of x over
X g dash of x.
exactly. Now just put
G
right because you
of
know
x
all
put.
the answers over here. The substitute we'll get.
Yes, sir.
Similarly, you can also solve for this. This is a composition, right? So my t derivative of x would be what? Derivative of f product. I hope you get this. What is this? The chain rule, right? This is what you said.
Yes, sir.
And similarly, you can also solve this. So yeah, this is also done. Like this was done. We'll start from ninth, okay? From next session, we'll start from ninth.
Okay, sir.
Anything else that you want to share with me? There are so many good questions that I want to discuss. For example, this is a really good question. I'll try to solve this problem in the next session.
Yes, sir.
Anything? Okay, then we'll close the session now.
Uh, okay, sir.